welcome everyone to the Shannon channel. I'm Salim Al-Roihib, and I'm really happy today to have Ayfer Ozgur from Stanford. And I'm really looking forward to her talk today on distributed estimation under communication and privacy constraints.
Well, thank you, Salim, for inviting me to speak here. So in this talk, I would like to tell you a little bit about this research line that I've been interested in now for a couple of years. So we'll talk about distributed estimation under communication and privacy constraints. And here we are motivated by distributed or federated learning type systems where we want to learn a centralized model for data that's distributed or maybe generated across a large number of nodes in a network. And this data can be images taken by mobile phones, can be text messages, can be speech recordings. And it's now well recognized that there are kind of two main challenges in implementing these kind of systems. The first one is communication. The training of these central models has to happen over bandwidth limited links. For example, in the case of federated learning, these nodes are mobile phones. The communication has to occur over wireless links, which typically have lower bandwidth. So communication here can easily become a performance bottleneck. And the second challenge is privacy. So if these are images you take with your phone or text messages you type, right, they will typically contain a lot of sensitive and personal information. And you don't want that personal sensitive information to be moved around in the network I should say, as you learn these models, you want to make sure that you don't leak too much information about the underlying user data. And if I have time towards the end of the talk, I plan to tell you a little bit about how people implement these systems. But before that, I guess as information theorists, we would want to somewhat understand this problem, study this problem from a bit more fundamental perspective, okay? And what is the fundamental question here? Well, we have distributed data, right? And we're trying to learn a model for this data, but we are subject to constraints. We have communication and privacy constraints. And then the question would be, under such constraints, how well can you learn? How accurately can you learn a model for your data? Or equivalently, what are the trade-offs here? What is the trade-off between the accuracy with which you can learn the model and communication bandwidth and privacy? And to get some insight about these trade-offs, we will take a statistical estimation approach. So we will assume that we have n nodes in a network, and each of these nodes observe a sample, an IID sample from an underlying distribution that's parameterized by theta, and theta is unknown, okay? And our goal is to learn the parameters of our model. And again, we are subject to constraints, and I'll tell you in a second how we exactly define these communication and privacy constraints. Okay, for now, our goal is to learn theta, right? We'll measure performance. We'll assume that we are given a loss function L, which measures the error we make if we estimate theta as theta hat. And note that theta hat here, our estimate will be random, right? Because our estimate will depend on the samples, random samples we get from this distribution. So for a given estimator, for a given scheme, we would like to look at its average error. And this is the average error we make when the true parameter, when the true distribution is p theta. And we'll take this minimax worst case approach. So if you give me any scheme here, any estimation scheme, which would be a combination of a kind of communication and estimation, I will look at the worst case performance of the scheme, overall possible realizations for theta. And I should say that theta here is not scalar. What we usually have in mind is these high dimensional settings where your model here can have many parameters that you need to estimate. So D here can be large, comparable to the number of samples you have. And two kind of canonical examples for this setting would be discrete distribution estimation and the Gaussian location model. So for discrete distribution estimation, we assume that the underlying distribution is discrete, and the only thing we know about the alphabet, the distribution, is the alphabet. Okay. So we have an alphabet of size D, and what we need to estimate are the probabilities of the different symbols. So we have D parameters to estimate. And in the Gaussian mean estimation model, so here you simply assume that each one of these samples here they come from a Gaussian, D-dimensional Gaussian distribution. So these are vectors, real vectors of length P. And now let's say you fix the covariance structure of your model. Let's say it's identity, and the goal is to estimate the unknown mean. Again, we have D parameters to estimate. Okay, and I should say that in recent years, people have also been interested in distribution-free settings. And what this means is that, so now I don't want to impose any probabilistic assumptions on how this data is generated. So I would just say that I have some data, some samples at these different nodes. And the only thing I know about these samples is that they live in a certain space, okay? And what I would like to do is I would like to estimate a certain function of these samples. And again, we'll have this minimax framework. So if you give me an estimator, a scheme, I will look at its worst case performance over all possible values for these samples. And maybe you can say, what is the expectation here? Because this is a distribution-free setting, right? There are no probabilistic assumptions. So the expectation here is over possible randomness in your algorithm. So you can have kind of a randomized strategy here, and you will look at the average performance over algorithmic randomness. And again, two canonical examples for this would be somewhat the counterparts of what I mentioned in the previous slide, would be frequency estimation or empirical distribution estimation. So in this case, you assume that all these samples live they come from a discrete alphabet. They take values in a discrete alphabet, again, let's say from 1 to D. And what I would like to learn this time is the empirical distribution of these samples.
I just have a question. Could we
Sure.
Yeah. So in your formulation for the problem, you chose to minimize the maximum over X, and so usually we have the empirical mean. What is the difference like here? So usually what we have is the empirical mean over all the data samples.
I'm not sure I understand the question. Okay, so are you asking, so basically here, what I assume is that I just have an alphabet, okay, a space, numbers from 1 to D. These symbols here can take values in this alphabet, and they're arbitrary. There is no probabilistic assumption. I don't assume anymore that they come IID from some unknown distribution. They're just arbitrary, and they will have some empirical distribution, right? And my goal is to estimate that empirical distribution.
Okay.
Okay, sure. Whereas in the previous case, we were trying to estimate, we made a probabilistic assumption. We assumed that our samples come from an underlying distribution, and the goal was to estimate that underlying true distribution. Certainly very related, but maybe slight difference. Okay, and similarly for mean estimation, right? So here you can say this would be another kind of canonical example of interest here. You assume that you have these, at each node, you have, let's say, a vector, a real vector of length d, and we will assume that these vectors lie in the d-dimensional unit ball. And my goal is just to estimate the mean of these n vectors, okay, this quantity here, mean estimation. Okay, and let me maybe tell you a little bit about how we model communication and privacy constraints. The simplest way to, I guess the simplest way you can model communication constraints would be to say that each sample here that I have at each node has to be encoded into a fixed number of bits and then communicated to the central node, okay? And the encodings at different nodes have to be done independently. Or you can also study kind of more sophisticated models that allow for some interaction between the nodes. For example, you can think of a sequential model where maybe these nodes transmit in a certain sequence, and then the transmissions are broadcasted. So now the encoding of the ith node here of its sample can depend on what it hears, what this node hears from the previous transmission. This will allow for some sequential interaction between the nodes. Or you can also study like fully interactive models where you allow these nodes to communicate their samples in a fully interactive fashion, typically by writing bits on a publicly seen blackboard. But again, you want to limit communication by saying that each node can write at most k bits on this final blackboard. I should say that, as you will soon see, there are kind of two different angles to these problems, right? There is the achievability side. We want to develop good schemes. And when we develop schemes, obviously we want them to be as simple as possible. So they will typically use just independent encodings at different nodes. But there are a few settings where we need some interaction, sequential interaction, to achieve the optimal error. But when we prove impossibility bounds, we will prove them under this most general model, this interactive model. And when the upper and lower bounds match, this essentially says that even if you had interaction, we allowed for interaction between nodes, you couldn't do any better than the proposed possibly simpler scheme, okay? Okay, so this is how we think about communication constraints. And how do you think about privacy constraints? So when we have privacy constraints, we would rather say basically the encoding at each node here has to be done by an epsilon differentially private mechanism. And what does an epsilon differentially private mechanism mean? So Q here is simply a mapping of the observations here to some output space, and the output space can be arbitrary, but we want this mapping to be such that the probability of any output symbol shouldn't change too much given the input symbol. Okay, so this ratio here has to be bounded in this fashion where epsilon is the exponent here. And this ensures that your output symbol doesn't leak too much information about the actual sample. Okay, and I should say that we are not the first ones and the only ones to look at these kind of settings. There is quite a bit of work in the literature at this point, especially over the last couple of years. And people have looked at kind of these kind of settings under communication and privacy constraints, typically separately, either communication or privacy. And over the recent years, there has been also interest in these distribution-free models that I mentioned. So we also looked at quite a few settings right now, so including this discrete distribution estimation, more general parametric models, non-parametric estimation, logistic regression, and also some of these distribution-free models here. So what I would like to do in this talk is to focus on two things. I would like to highlight two contributions, one from the achievability side and one from the converse side. On the achievability side, even though there are now optimal schemes, schemes that achieve optimal accuracy under either constraint, privacy or communication, there is not really much work about achieving optimal accuracy when you have both constraints at the same time. You see that basically the answers there don't simply follow from what we already know about each constraint separately. So this is what I would like to highlight on the achievability side. And on the converse side, I would like to tell you a little bit about this kind of framework we develop, which relies on Fisher information, which allows us to get tight bounds for essentially all these settings that I mentioned in a unified and kind of very, I think, simple way. So I'll talk a little bit about that. Okay, and let's start with achievability. So for achievability, I thought I would focus only on one specific setting here. And the simplest setting to discuss is this discrete distribution estimation. So that's what I will focus on the achievability side. Okay, what is discrete distribution estimation? So just to recap and make sure my problem setting is very clearly defined. So now I have an unknown distribution. I know the alphabet, let's say just numbers from 1 to D. And I have n nodes, each of which observe an IID sample from this unknown discrete distribution. And they have k bits to communicate their sample. Whatever sample they have has to be communicated into k bits. And then, sorry, is this disturbing? Okay, maybe I'll hope I don't get too many emails during the talk. Okay, and then, okay, the nodes encode their samples into fixed k bits. And then the estimator has to output an estimate for this discrete distribution based on this k bit messages, okay? And here I would like to focus on L2 loss, L2 error. So if my distribution is, my true distribution is P and I estimate it as P hat, the error I make is the L2 distance between these two distributions. And what our results also extend to kind of L1. We also have results on L infinity, which relates to heavy hitter estimation. But for simplicity, this is the kind of the metric, the error metric I will focus on in this talk. And again, sorry, go ahead.
So when you say, I think you're explaining it, you mean like the L2 distance? It means like between the estimated probability for the individual I and the true one?
Yes, essentially this formula here, right? Okay. So basically think of the distribution as a vector of length d, right? Mm-hmm. Both the estimated and the true distribution, and essentially is the squared L2 distance between these two vectors.
So why aren't you using like the usual metric for distance between two distribution, like for example the KL divergence or the total variation distance, or these metrics? Why are you
usually for distribution estimation, the more meaningful metric is actually L1. And actually our results, what I say applies almost as it is to L1 as well. So it doesn't really change the discussion too much. About these other measures like KL and total variation distance, I should say we haven't really looked at them very carefully.
I think the total variation distance is L1. I think this is.
Yeah. We looked at L infinity also, I think. Yeah.
Yeah. Okay. I see. Okay. Thanks.
Sure. And now, okay. So let's see. And as I said, the estimate is random, right? So we take an expectation here. And then again, we'll take this worst case approach. So if you give me any achievable strategy here, and now this communication, this encoding of the samples and the estimator can be jointly designed. But if you give me any particular scheme, I'm looking at its worst case performance over all possible distributions on an alphabet of size D. Okay, so this is our setting. So what do we do? Okay, maybe let's first just think about the classical case, right? You just have n samples from an unknown distribution. How do you estimate distribution? So the most natural thing to do would be to estimate basically just to compute the empirical frequency of each symbol in your alphabet, and then take that as an estimate for its true probability, right? And if you do that, you can easily do the kind of calculation, and you'll see that the L2 risk that you will get with this strategy in the centralized case would be 1 over n. So it will be inversely proportional to the number of samples you have. Okay, and but okay, we are in this kind of communication constraint case. What do you do when you have a fixed communication budget to communicate each sample? Obviously, if k is equal to log d, larger than log d, then you're fine, right? Because you know that your samples come from an alphabet of size d, so you can communicate them as they are. But what happens when k is smaller than log d? And for this, you can consider this kind of very simple strategy. You take your alphabet of size d and you partition it into subsets of size 2 to the k, okay? And now how many subsets do you have? D divided by 2 to the k, okay? And now you will assign each subset to one node. So you have n nodes, m subsets. So each subset will be assigned to n over m nodes. And now, what do the nodes do? Well, they will be only responsible for signaling the symbols in their assigned subset. So they look at their sample. If it's one of these 2 to the k symbols, they will signal that to the server. And if not, they'll simply discard their samples. Server will look at the empirical frequency of the symbols that were signaled to it. And if you think about this essentially what this is doing is, this is reducing your effective sample size from n to n over m, because now each symbol in this alphabet can be potentially signals observed just by n over m nodes. It's as if you have n over m nodes, effectively, n over m samples. So this is now your L2 risk, okay? And turns out that even though the scheme is somewhat simple, you can show that you cannot do better than this, okay? So even somewhat the constants are quite close here. And this is basically saying the following. So this is saying that when you're communication constrained, especially when k is small here, you have this additional factor of d here as compared to the centralized case, right? There is this penalty, and in high dimensional settings, if d is large, this can be very significant. But maybe the good thing is that this penalty decreases exponentially in k, and when you have log d bits, you're back in the centralized case, which is trivial, of course. So maybe the more interesting thing really about this result is how you prove optimality, how you develop the lower bound. And I'll talk about this a little bit in the second half of my talk. But before that, I would like to tell you a little bit more about achievability here.
So I have a quick question. So for how many bits, what's the budget bits here?
Say again, sorry.
Yeah, how many bits here you're transmitting per user or per sample?
K bits.
K bits, oh, okay, okay.
Yeah, k is the number of bits.
Okay.
So this is my setting.
Okay.
I forgot to emphasize that. Yep. So k bits, and once you have log d bits, you see here, right? Basically, then the error you get is 1 over n, so you are back in the centralized case.
Do you think it's interesting to look at the case where there's some correlation between these samples? Because then you can like.
Yeah, I think it's definitely interesting. But from what we have so far, yeah, I don't know how we would handle that. Yeah, but
because there's no way to resolve within a bin, right? I mean, the point that suppose you assign me a bin and I just report whether I have it or not, but that's the only information you can get about it. There's no way to get any more information. I'm just thinking if maybe if some other user observing some correlated version, you can just narrow it.
Yeah, especially it might be interesting. Yeah, I definitely think it's interesting. It might get even more interesting if you somewhat have some of these more interactive models where somewhat you can also, because that's also practically kind of relevant, like you have some interaction and then maybe you can exploit that to be much more efficient. Okay, so how about privacy constraints? This was about communication constraints. So what is the setting here? The setting is exactly the same. We are still trying to estimate this unknown distribution, but now I will change the constraint on these encodings here, okay? Instead of these encodings being limited to k-bits, k-bit outputs, I will say the encoding at each node here has to be done by an epsilon locally differential private mechanism. And what that means, again, is basically what is written here. The probability of each output symbol shouldn't change too much, or is limited in terms of how much it can change given different input symbols. Okay, and again, same error criteria. Okay, what happens in this case? It turns out that actually people have looked at this discrete distribution estimation under privacy constraints earlier than kind of our previous work, which looked at this problem under communication constraints. And in the case of privacy constraints, there is this paper, for example, here, which looks at randomized response for this problem. And randomized response simply means the following. So you take your observation, your sample, and you either transmit it as it is to the server with some probability, or with some other probability, you flip to one of the you flip it to one of the remaining d-1 symbols in your alphabet. Okay, so you either kind of transmit it as it is, or you change it to one of the other d-1 symbols. And the probabilities here will have to be tuned to the privacy level you want. Turns out that this is optimal in some regimes, but it's not optimal for all epsilon regimes here. And there was a follow-up paper by Ye and Bark here, and they introduced the subset selection mechanism, which can be viewed as a generalization of this randomized response. And this one turns out to be optimal for all regimes, and they characterize the L2 risk as being this one here. Okay. And if you look at this formula, you see that a similar thing happens with privacy constraints, right? So if epsilon is small, and this will be the high privacy regime, you see that there is a factor of D penalty here again, as compared to the centralized case. Okay, and now the remaining question is what happens when we have both of these constraints? Typically, we want both. We want both privacy and communication efficiency. Can we get this by simply taking the optimal schemes developed under both constraints and somewhat concatenate them? Turns out that this is not okay. This doesn't work, because if you just do that, then you get essentially penalized twice. Once for the communication constraint and once for the privacy constraint. So you have to be a little bit more careful here and somewhat design your scheme from scratch by taking into account the fact that you have both communication and privacy constraints. And this is what we do in this more recent paper here, where essentially we show that if you do this, if you kind of design a more careful scheme here, you don't have to suffer from this double penalty. And essentially, your performance will be dictated only by the more stringent constraint, and you can satisfy the less stringent constraint for free. That comes for free. So you see here that this D-square penalty is now reduced to just D, as was the case with a separate privacy or communication constraint. Okay, and I would like to tell you a little bit about this scheme, which is a bit more sophisticated than the previous schemes I discussed. So in order to achieve this performance, we will make use of this Hadamard transform or Hadamard matrices. Okay, so okay, so so what is the Hadamard matrix? This is a matrix that has entries -1 and +1. And you can construct it in a recursive fashion by taking this recursion. Let's assume D is equal to 2 to the m for simplicity. Then you start with H1 is equal to 1, and you take this rotation, recursion, and you end up with a D times D matrix of -1 and +1s. And this matrix will have some very nice properties. Like its rows and columns will be balanced in terms of the number of +1s and -1s. They will be orthogonal and so on. Okay, and the main idea here—
I'm sorry, sorry to interrupt. I have a question. So here you're looking strictly at non-interactive models, right?
I actually don't hear too well what is being said. Can you repeat again?
Okay. Sorry. So my question is, you're looking at non-interactive models in this result?
So here we are trying to develop a scheme, right? I mean, ideally we would want, it's easier to think about non-interactive schemes, right? Just independent encodings. So right now the scheme I will come up with will have no interaction at the end. But non-interactive really comes into play in our results more on the lower bound size, because you want to prove you want to make your impossibility results as strong as possible, and then we prove them for these interactive models. But this particular scheme, just like the previous schemes that I mentioned, will be non-interactive, won't make use of interaction.
Okay, thank you.
And here is the scheme. Here is our strategy. So we will take our observation, right, our sample at the ith node. And I would like to transform it before I try to communicate it. And for this, what I'll do is I will encode it in a one-hot fashion. That is, I have these symbols in my alphabet, right? I will encode them as d-dimensional vector consisting of zeros in all but one location. There will be only a single one in one location, and that will indicate the corresponding symbol. So I take this one-hot encoding of each of my observation, and I multiply it with this Hadamard matrix. And then I get a vector again of length d, but now will be, its entries will be plus or minus ones. And my goal is to communicate this transformed observation to the central server. Okay, what if I cannot communicate it as it is? Let's say I have a communication constraint. Let's say I can only communicate 1 bit about this transformed observation. Then each node will pick just one location, one entry, and will communicate the corresponding entry with a single bit. Okay, and if you want privacy on top of that, when the node communicates that bit, it will use something like randomized response, meaning that it will either flip that bit. It will either send that bit with certain probability or flip it with the remaining probability. Okay, and then once, what do I do at the server? At the server, somewhat, I will try to, roughly speaking, first try to estimate the ZIs, the observations, and then I'll take an inverse Hadamard transform, and I will estimate the XIs, and from that I will go through to an estimate for the true probability. Okay.
So what is the intuition here of using the Hadamard matrix?
The intuition is the following. So if you look at this if you look at the one-hot encoding of your symbol, the XI, right? So now the probability that you look at your one-hot encoded observation. So in this case, each entry can be 0 or 1, but the probability that it's 1 will probably be very small. If you pass now each entry independently through a noisy channel, you will essentially lose your signal. The noise will harm you too much, the noise you introduced due to privatization. But if you take this transform, now each entry here will be, regardless of the distribution, will be equally likely to be plus or minus. You're essentially spreading the information in multiple dimensions now. and it becomes more resilient to noise you introduce by privatization. That's the main idea. And this scheme is actually not new. This appears in this ICML paper from last year. But this is a scheme they developed only for this 1-bit case. So when you only have 1 bit per node, this is what you can do. And turns out that this is optimal when you need high privacy. Okay. But obviously, normally, right, we want, we want to be able to have an optimal scheme for any bit budget and any privacy level. So we want to extend this to an arbitrary number of bits. And that's non-trivial somewhat because if you have more bits at each node, I guess the straightforward idea would be just to try to communicate information about more entries in ZI, right? Maybe I pick now K entries and I try to communicate those K entries, but this will lead to a performance where your error will decrease linearly in K. And if you remember kind of our formulas from the previous discussions, actually our risk here was decreasing exponentially in K. We want the error to decrease exponentially with the number of bits we have. So we'll have to be a bit more careful. And for this, we'll have to make use of this recursive structure of the Hadamard matrix. And what I mean by that is the following. So let's say I have D is a power of 2, right? Let's say I decompose it in this form, 2 to the K minus 1 times B, and B will be a power of 2 as well. So now a Hadamard matrix of the dimension D times D, can be written as the Kronecker product of these two Hadamard matrices of dimension 2 to the K minus 1 and B here, okay? And pictorially, what this means is that if K is equal to 3, right, this first one would be H4. So this is saying that your Hadamard matrix can be represented in this block structure here, okay, with HP repeating here with the corresponding coefficients plus or minus 1. And now our strategy will be the following. We'll also chop this 1-hot encoded xi vector into 2 to the K minus 1 blocks, okay? And instead of trying to communicate ZI directly, I will try to communicate HB times this corresponding vector, okay, XIL. So essentially HB times XI1, HB times XI2, and so on. And these are all basically vectors now of length B, and I have 2 to the K minus 1 of these vectors. Why do I do that? Because this is sufficient information to reconstruct ZI, right? Because I know the Hadamard matrix has this particular structure. And this can be communicated more effectively, because if I wanted to communicate ZI as it is, this is of dimension D, of length D, which is this product, and I need D bits, which is this product here. But these are vectors. I can communicate these more efficiently because of the following. I know that this is a 1-hot encoded vector, right? So it only has a 1 in a single location. So only one of these vectors will be non-zero. And in order to communicate this whole collection, the only thing I need to do is to communicate the index of the non-zero vector. And this requires K minus 1 bits because I have 2 to the K minus 1 such vectors. And then I'll communicate the value of the non-zero vector. And you see that there is this decrease from something exponential in K to something linear in K. Okay, and this is essentially the key idea we use. And obviously, if you don't have sufficient bit budget to communicate all this information here, that is this much bits, then what you will do is each node will just communicate one row of these vectors. So let's say the first entries of these vectors, and that requires exactly K bits. So it's as if B is equal to 1 here. And then you privatize with this randomized response, which it's not optimal in general, but turns out that if you take this Hadamard transform, applying randomized response at the end is without, doesn't lose you any optimality. Okay, and this is essentially the main idea of the scheme. It uses this recursive, this particular structure of Hadamard matrices. make things a bit more efficient. Okay, and I should say that we have looked at now a number of settings under joint privacy and communication constraints. A setting that has received some interest over the recent years is this distribution-free mean estimation that I mentioned in the beginning. Remember, you have this n vectors, d-dimensional vectors lying in this unit ball, and you just want to know their average, right? Their mean. And again, there has been some work on this, on the setting under separate differential privacy and communication constraints, but not really too many works that try to do the two at the same time. There's one work I would like to mention. So this is a recent paper, BQSGD, where they look at both constraints at the same time, and they come up with a scheme which
we have Ayfer.
Sorry?
We have that talk on this paper on the channel.
Oh my God. Okay, good. So hopefully I'm not saying something wrong about their paper. So the people who listen to this talk can go back and check. Okay, so I will claim that they have a number of schemes, but somewhat most relevant to us here. It applies in this particular regime, okay, some regime of epsilon and k. But the error they get is this d square n, which I would say is not too good, because it suffers from this double penalty that I mentioned before, right? You have a d square here. This is somewhat like almost equivalent to the baseline where we were just putting the two optimal schemes back to back. Whereas what we are able to show here, we develop a scheme which can applies for any privacy. It's applicable at any privacy level, any bit budget. And then this d square here becomes d, and you have the same flavor. So you're only penalized by the more stringent constraint, and you can get the other one for free. But you have to do the encoding again carefully. It's a different scheme for this particular setting. Okay, so let me see. I'm quite okay. I'm going slower than I thought. So maybe I'll just tell you a little bit about the other side of things, impossibility results. How do you prove impossibility results for these settings? So for this, we will need to let's think about how we prove impossibility results in statistics, right? So we are interested in this parameter estimation setting. And again, just to recap, we have an underlying unknown parameter theta. We observe a sample from a distribution that depends on theta, and our goal is to estimate theta, let's say, by minimizing this error here, the mean squared error. And then one of the most famous results in statistics is, I guess, this Kramer-Rao lower bound, which says that any unbiased estimator for theta in the setting will have to have a mean squared error that's lower bounded by the inverse of the Fisher information associated with this model. And Fisher information can be defined in a certain way. You typically first talk about the score of the model. That's just kind of the derivative with respect of log of this density here. And then you, if you plug in x here, this will be a random variable. So you just look at its variance, and that's Fisher information. Maybe the math is not so important. Essentially, it quantifies how informative a sample from this distribution is regarding the underlying parameter, okay? And turns out that in order to prove tight lower bounds for the settings I discussed, you need to look at a somewhat natural extension of this basic parameter estimation setting. You have to study the following problem. Let's say now I have a parameter theta. I have a sample from a distribution that depends on theta. But then I don't have access to x directly. I just have access to a privatized version of x, a k-bit quantization or an epsilon privatization of x. Okay, and now the question is, how large can Fisher information from this quantized or privatized sample be? Okay, can we characterize that maximal Fisher information? Because if we have a bound on the Fisher information, then we can somewhat plug it in here in the lower bound in a somewhat similar fashion. I'm ignoring details a bit, but that will essentially give us what we want. Okay, and that's precisely what we do. We essentially characterize this maximal Fisher information here. How large can this Fisher information be under k-bit communication and epsilon privacy constraints? And maybe one detail I skipped is that, remember, in our models, we usually don't have a single parameter, scalar parameter here, but we have multiple parameters we want to estimate from X. And in that case, you can actually define multiple Fisher informations, each quantifying how informative your sample is regarding the corresponding parameter. And then the thing you need to control turns out to be the sum Fisher information. Essentially, we are able to characterize the sum Fisher information, the maximal value this sum Fisher information can take, as a function of the underlying model. So it turns out that the impact on epsilon and k on the sum Fisher information here will really depend on the underlying statistical model, the problem you're trying to solve. So you can, once you're given the model, you can easily compute the score function associated with this model, the score random variable. And then you need to look at basically its tail behavior. So if this random variable has finite variance, then you can immediately show that the Fisher information not be larger than essentially these expressions in the privacy and communication case. If you have a bit more control, if this score random variable has a sub-Gaussian tail, then you can bound these Fisher informations with a linear function of epsilon and k respectively. And then, yeah, you can also have this quadratic behavior. Okay, so the dependence on epsilon and k is dictated by the tail behavior of the score random variable. And once you have these characterizations, essentially you can apply this framework in a quite straightforward way and in a unified fashion to all these models that I discussed. Essentially, the only thing you need to do is to compute the score associated with each model, look at the tail behavior, and plug in the corresponding bound for Fisher information. And that's how we obtain the tight lower bound for distribution estimation with k-bit constraints. In the case of privacy, the bound was proven in previous works here, but you can now recover it in a similar fashion. You can recover bounds that were proved for this Gaussian location model with epsilon local differential privacy or under k-bit communication constraints. Essentially, I guess the message I'm trying to convey here is that in most of this prior work, when people develop impossibility results, they usually focus on a certain model or certain class of models like either discrete distribution estimation or Gaussian location type models. But now all these lower bounds can come essentially from the same framework. And you really see what is it that dictates a certain behavior, what are the right conditions that lead to exponential, quadratic, or linear behavior in epsilon and k. And you can uncover kind of like interesting behavior, like there are also some models where in a certain regime, the dependence would be exponentially on epsilon and k, and in some other regimes of the parameters, you'll get linear dependence.
So Ayfer, is this does this kind of converse bound also apply for the non-Bayesian case? Because you mentioned the case where
then there is no distribution, right? At all. The distribution-free case.
Yes.
It does essentially. There is an extra step that you need to take in order to connect basically the distribution-free setting with this probabilistic framework. But that's a pretty simple step, and then you can essentially take this machinery and apply it there. It's
because in this case, the randomization is coming from your private mechanism.
Yes. Okay. And actually, this is one thing I kind of forgot to mention. So for example, for this discrete distribution estimation, we talked about one particular strategy, right, based on this recursive Hadamard response. You can also apply that to the frequency estimation case when there is no randomness. But in order to apply it, you will need some private randomness, access to some shared randomness among the nodes. They're slightly different, but there are obviously a lot of similarities between this distribution-based and distribution-free model.
So if I understand correctly, the Kramer-Rao bound, you can use it to recover other results in the literature as particular cases. But what is the tool there that they use for the converse? So
you mean the other works?
Yeah. So what is mainly the main tool they use? Like
there are a couple of methods. For example, one of the methods is based on Fano's inequality. So basically, you convert the estimation problem into a hypothesis testing problem. You construct a certain hypothesis, and then you apply Fano's inequality, and then you have to control the mutual information. I would say this is also how we first derived our lower bounds. Things can get pretty complicated, and also they're usually specific to the setting. So I would say that what we do here, I think, is much simpler, and it kind of works nicely across all these different problems. They also use, like, in order to control the mutual information, once you apply the Fano's inequality, they would try to develop strong data processing inequalities. But strong data processing inequalities, essentially, if you take that path, you usually end up only with a tight bound when the true dependence on epsilon and k is linear, because you bound one mutual information by some other mutual information times a linear coefficient. So it's somewhat, there are different approaches. Okay, and I guess I'll stop here. The only thing I wanted to mention at the end was basically, this was more like a fundamental perspective on these distributed learning, federated learning type settings. And I wanted to say a little bit about, like, how you could potentially take insights that emerge from this kind of a theory and try to apply them to the way people actually implement these systems, which is by using kind of distributed SGD and empirical risk minimization. And I think there are some interesting things that can be done there, basically, to bridge this kind of theory, insights from this kind of theory, and use the insights to improve the efficiency of actual SGD algorithms. But maybe I'll leave that to another day, okay? And I'll stop here. So thank you.
Thanks a lot.
Yeah, thank you for listening. Yeah.
Thanks a lot for the great talk. And I think we asked lots of questions, but I don't know if there's still anyone who has questions. So maybe I'll start. So in terms of open problems in this area, so anything in particular you think is interesting? Because I can see there's lots of work from the theory on our side, but also on
Sorry, I couldn't follow the question. Say again. I got, yeah.
Oh, okay. So I'm saying I want to get your opinion on open problems in this area, and also because I know, like, I mean, we're bringing theoretical tool to this area, and also there are lots of work from more machine learning practical on how to quantize or these things. So how do you see this kind of, like, in terms of open problem, in terms of like these two approaches meeting?
Yeah. I think that's a very interesting direction, and that's exactly what I was kind of trying to touch upon a little bit in the third part. So there are two different approaches, right? There is more like an optimization kind of perspective on these problems. So you say, people do distributed SGD in this kind of systems, and one line of work typically does the following. You come up with some heuristic way of quantizing or introducing privacy, and then you're trying to prove that given that modification, which will introduce the communication load, let's say, your algorithm, your SGD algorithm will still converge, or its convergence rate wouldn't be harmed too much. That's one direction we take. So what this one here that I described is more like the statistical approach, we kind of assume that there is a statistical model, and then you're looking for the right solutions for that statistical model, right? What is the best way to get communication efficiency, privacy, given that statistical model? So one route you can take here is, and this is what we were trying to do here in the class part, you can say, can I maybe model the statistics? Can I come up with a suitable statistical model for how these gradient vectors behave in distributed SGD? And then somewhat analyze the theory and then use the theory-inspired schemes in order to reduce communication bandwidth or make things more private. And I think there is a lot of hope in that direction, but it's very, I don't think there is not much. So we have one attempt basically, but I think there is much more that could be done in order to bridge basically, in order to take this kind of work and see what kind of insights they can suggest for these optimization algorithms.
Perfect. Thanks again, Ayfer. I really enjoyed it.
Yeah, thank you, Salim, for having me.
Many people
here.
watching on YouTube also.
It was a pleasure. Yeah.
Yeah, thanks. Bye-bye.
Take care. Take care, everyone.